Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present UV curable epoxy resins. When compounds containing double bonds are exposed to high-energy electromagnetic waves, a rapid crosslinking occurs. Unsaturated polyesters and resins with acrylic groups can be used for this purpose. Radiation curing happens through UV curing or electron beam curing. The crosslinking by radiation happens either through ionic or free radical mechanisms. In the case of UV curing, the photoinitiator is exposed to light and generates free radical or cations which initiate crosslinking. However, in electrobeam radiation cure, the high-energy electrons interact directly with the unsaturated sites and highly reactive molecules are generated. UV curing of epoxy systems might happen through a free radical mechanism or through a cationic mechanism. The free radical mechanism, which is more common, has 4 steps: initiator radical formation, initiation, propagation, and termination. These steps have been illustrated in this figure. In the first step, photoinitiator decomposes on exposure to UV and initiating free radicals are produced, which starts the chain reactions. Here, quenching or deactivation of the photoactivated initiator by oxygen can occur, which result in short polymer chains, tacky surfaces, and poor mechanical properties of the coating. However, often the propagation rates are high and oxygen quenching is minimized. The cationic cure mechanisms involve the photogeneration of ions, which initiates ionic polymerization. Oxygen inhibition is not happening in cationic cure mechanisms, and they generally provide less shrinkage. However, the photoinitiators are sensitive to moisture and other basic materials. Therefore, most UV curing systems are acrylate-based, which are cured through a free radical mechanism. Acrylic-based resins for UV curing are polymers or oligomers that contain unsaturated acrylic groups, either acrylic acid or methacrylic acid. Acrylic acid or its esters induce more reactivity to the resin and therefore are preferred over methacrylic acid or esters in UV curing systems. The following acrylate resins are technically in use: epoxy acrylate, polyester acrylate, polyether acrylate, polyurethane acrylates, unsaturated acrylic resins, and silicone acrylates. Epoxy acrylate systems have been introduced in another video in details. They are produced by the reaction of epoxy resins, aromatic types containing bisphenol A with free radical acids. Different epoxy acrylates that are commonly used for UV curing adhesives or coatings have been presented here. The epoxy acrylate formulation are used in UV paints which confer high reactivity, hardness, and excellent chemical resistance. Various types of epoxy acrylates can be cured by UV curing, including aromatic difunctional epoxy acrylates, acrylated oil epoxy acrylates, novolac epoxy acrylates, aliphatic epoxy acrylates, and miscellaneous epoxy acrylates. However, as explained earlier, they do not show good weather resistance and also they exhibit yellowing. In most UV curing systems, the UV light reacts with UV initiator or photoinitiator to generate free radicals, which in turn trigger the polymerization. Sensitizing might be necessary to be combined with the UV initiator in UV curable systems. Free radicals can also be directly generated by high voltage electron beams and used in free radical polymerization, which yields a cross-link molecular network. In this process, there is no need to use initiators. UV lights are electromagnetic waves with wavelength ranging from 100 to 400 nanometers. UV light can be used to activate the chemical bond reactions, as UV photon energy is in the range of 300 to 760 kJ per mole, suitable to activate corresponding chemical reactions. It must be noted that the energy of UV radiation with wavelengths of 100 to 280 nanometer is very high, as it is often absorbed by the upper layers, which leads to an incomplete cure in the lower layer of the film. Therefore, UV light of longer wavelengths, for example 315 to 380 nanometer, is preferred for UV curing. The UV initiators, sometimes in combination with UV sensitizers for generating the free radicals, are required for starting the reaction. Here, oxygen can act as an inhibitor for the polymerization, which is more effective at the upper layers. In practice, a combination of UV lights, mainly with long wavelength, 315 to 380 nanometer, and a smaller amount of shorter wavelength, for example, below 350 nanometers, are used for UV curing. By this strategy, the inhibitory effect of the oxygen at the surface and upper layers will be compensated. Photoinitiators and sometimes photosensitizers are used to compensate for the lower energy density of UV light, which is initially inadequate for the polymerization reaction. The UV absorber or sensitizer is transformed into excited sites after absorbing the UV light, which subsequently forms free radicals by cleaving of the bonds or by the adding of the hydrogen atoms. Free radical polymerization is then initiated at the double bonds with the aid of the free radicals. The reactions involve initiation, chain propagation, and chain termination. UV systems, so-called 100% systems, are cured very fast by irradiation of UV light from various UV emitters. In these systems, often no solvent is presented, and so there is nearly no emission of the volatile organic compounds, which is crucial from environmental point of view. However, some of the ingredients of UV systems could be a health hazard. UV light leads to the production of ozone, which also has to be exhausted carefully. Moreover, heat may evolve during the UV curing, which may promote the evaporation of the UV system contents. Because of their viscosities, solvent-free UV systems are often used in an automated continuous roller coating or a curtain coating of planar objects, wood plates, laminate sheets, foils, etc. And there are only a few instances of spray applications. A schematic diagram of the typical equipment is presented here. UV emitter is the most important part of a UV curing process and is the energy source of the UV light. The UV can be generated in wavelength in range of 200 to 760 nanometer by high pressure and medium pressure mercury lamps, microwave UV radiators, electrodes vapor lamp, pulse xenon lamps, or lasers. The choice of UV lamp depends on the application, whereas the UV curing is influenced by the radiation energy, light spectrum, and exposure time. These sources often produces a certain degree of infrared radiation as heat, which is beneficial for the annealing of the cured coating, relieving internal stresses and strains, or enhancing the cure rate in cationic cure systems. UV initiator absorb UV light and form excited bound states, which in turn produces free radicals. UV sensitizers also absorb UV light but transfer the absorbed energy to other molecules, which can cleave into free radicals. Different classes of UV initiators have been developed for different applications, generally based on their reactivity. The choice of UV initiator also depends on the solubility. It should be readily miscible with the UV system. Compatibility, storage ability in dark, yellowing resistance, health effects, and cost are other important factors. The simplest UV initiators are benzophenone and its alkyl derivatives, which can form free radicals together with hydrogen donors, mainly tertiary amines. For example, methyl diethanolamine, 3-ethanolamine. The combination of benzophenone and tertiary amine are inexpensive and yield a good surface cure. Their limitations are their tendency to yellowing and problems in fully curing thick layers. Benzoin ethers also form highly reactive free radicals, alpha cleavage, and are suitable for clear wood coating, but they are also poor storage stability and exhibit yellowing. Benzyl and its alkyl derivatives also need hydrogen donors, and they are capable of absorbing UV light up to wavelengths of 450 nanometers. And so, they are perfect for pigmented UV paints. However, their tendency to yellowing is comparably much higher, which has restricted their use. On the other hand, benzyl ketols are very reactive, since one molecule of benzene ketol forms 4 free radicals, which offer optimum cost effectiveness and exhibit much less tendency to yellowing. Benzyl ketols are cured effectively in thick layers and can be used for clear coats and wood paints. Alpha hydroxyalkyl phenols also have high reactivity. Liquid derivatives with aliphatic side chains are heat resistant and are more suitable for solvent-free paints. 1-hydroxycyclohexylphenyl ketone is an odorless solid and has excellent storage stability. The alpha-amino alkyl phenols with structures comparable to those of alpha-hydroxyalkyl phenol are suitable for pigmented UV systems. However, they have a more yellowing tendency. Benzoyl phosphine oxide, mono, and dibenzoyl phosphine oxides have been reactivity combined with excellent stability. The benzoyl phosphine oxide has been shown here. With the possibility of 2 types of cleavage, they have high free radical yields. Benzoyl phosphine oxides are suitable for pigmented UV systems. For UV systems, often reactive diluents containing monoesters of acrylic acid are used. Similarly, diluents with esters of methacrylic acid are not often used due to their lower reactivity and final cross-link density. However, low molecular esters of acrylic acid often have an unpleasant odor and evaporate relatively faster, which in turn imposes higher health risks. Therefore, suitable monoacrylate for UV systems are esters of acrylic acid and higher molecular monoalcohols such as octyl, decyl, phenoxyethyl, narbonyl, and dicyclopentadienyl acrylate. Hydroxyalkyl acrylate are also used as reactive diluent in UV cure systems. Acrylic esters of polyols such as hexanediol diacrylate HDDA, 3-methylol propane 3-acrylate TMPTA, pentaerythritol 3-acrylate PETRA, and pentaerythritol tetraacrylate PETEA are also an important class of reactive diluents for UV paints. In these systems, the ester functionality has an inverse effect on the diluent thinning effect. They have a relatively low vapor pressure and at ambient temperatures, but they can cause allergic reactions in the skin and cause sensitization, which has restricted the use. Concerning the health hazards, the esters of polyfunctional polyether polyols are less risky. This group include diethylene diacrylates, dipropylene diacrylates, acrylic esters of ethoxylated polyols such as glycerol, 3-methylol propane, di-3-methylol propane, pentaerythritol, and dipentaerythritol. Thanks to the mobility of the ether groups, polyether polyols confer optimum thinning properties, and the produced films are also flexible. However, the presence of the ether group impacts the weatherability. The cross-linking density in cured UV coating is generally higher compared to the most other crosslink films. The presence of a CC-bound network structure results in excellent chemical resistance to acids and bases. UV coatings have good mechanical properties and excellent scratch resistance. The final flexibility of the film can be tuned based on choosing resins and reactive diluents with different natures, which makes UV coating suitable for plastic parts also. However, UV systems are often used for wood coatings, for example, furnitures, parquet sailors, and laminate sheets. The process is especially suitable for generally planar objects. The other major applications include the coating of papers and foils, can coatings, and coil coating. UV curing printing inks and printing sealers and laminates also use this technique. On the other hand, the viscosity of UV paint is often not low enough for spray applications, and also as pigments often absorb UV light, the UV curing of pigmented systems is kind of problematic. Moreover, the radiation does not reach all the parts of complex objects uniformly, result in an irregular cross-linking which adversely affect the film properties. A technique called a dual cure can be employed to overcome the problem of application on three-dimensional objects. In this technique, cross-linking occurs through another supplementary reaction in addition to the UV curing. However, most dual cure systems are no longer solvent-free. Benefits of radiation cured epoxy systems have been presented here. Radiation curing of epoxy systems significantly reduces the cure times needed for conventional epoxies, which is crucial for adhesives. In adhesives applications, radiation curing provides high glass transition temperature, low shrinkage during the cure, no volatile emissions, excellent shelf life, and relatively low residual stresses. Moreover, for the adhesive applications, the absence of heat, water, or solvent in these coatings is a merit. Other benefits of the radiation curable adhesion have been tabulated in this table. The main disadvantages of a radiant curing epoxy system is their relatively high material cost, as these compositions generally have no cost components such as solvents, extenders, or fillers. Moreover, in the application of radiation-cured adhesives, to initiate the cure, radiant has to penetrate to the depth of the adhesives, and also at least one substrate must be transparent to the radiation energy. In other coating application, especially in complex geometries, shadowed area protected from the radiant energy create problems. In radiation curing, there are some main considerations, including type and source of radiation, nature of photoinitiator, and the resins to be cured, and final properties required in the cured product. The effect of radiation dose on the UV curing adhesive system is that as the dose increases, the molecular or MW increases. This consequently results in a decrease in a peel strain and an increase in cohesive strain. Chemical resistance and thermal stability of UV cured systems are also generally increased by a greater radiation dose. However, the fast curing in adhesives might be problematic. As in many radiation cured systems, the processing window is narrow. Therefore, there is a risk for undercure or overcure situations. Thanks for your attention. I hope you enjoyed the video. Please share your thoughts, questions, or comments, and I will come back to you soon. Thank you.